Now, we are going to go through a few terms related to queuing systems, which can describe a queuing system. First, clients and servers. Actually, these two words that you have already heard in several applications so far. So what do these mean? The term client is basically an official and general term which may refer to people, customers, vehicles, patients, pallets, airplanes, email, cases, orders, products. So whatever entity you are working with, whatever entity which is asking for a service in a queuing system is called a client. Okay, the clients are the entities which arrive to the queuing system and require a service. For example, the people who are going to a hairdresser shop and asking for a haircut are the clients of that queuing system. Vehicles would like to go through the bridge, so they get in the queue in front of the toll booth, and these vehicles, again, clients there. So patients who would like to get a healthcare service, they are clients. Emails, which are waiting in the server to be processed and directed to the destination, they are clients in that server. Now, the term server, it's a resource which provides the requested service. So the clients are getting the service from the servers. It's a resource which provides the requested service. The servers, they can also be defined as entities. For example, if you consider a hairdresser shop, the customers are entities of interest which are considered as clients because they would like to get service. However, you can also consider the servers, the number of employees who work in a hairdresser shop. Each of them can be considered as a server. For example, receptionists, repair personnel in a maintenance system, mechanics, medical personnel in a healthcare system, automated guided vehicles in a material handling system, or the machines in an automated storage and retrieval system. Okay, CPUs, central processing units, because, if the emails are entities in a communication system, then the CPUs, they are the servers, right? Because these CPUs are the ones who are going to direct a list of emails to the destination. Airport runways, if the airplanes are entities, airport runways, which are used for taking on and off, are the servers. So machines are the classical example for a server. So if you consider a banking system, a teller is a server and a client is a customer. So both items and services can be mobile in a system. So you see, there are some systems in which the clients are mobile and the servers are at a fixed location. For example, if you consider in a banking system, the clients are mobile, they are walking through the system, going from one server to another. Or if you consider a healthcare system, the doctors are waiting for examining patients in their rooms. They are at a fixed location. However, the patients are mobile. There are also other type of systems where the servers are mobile and the clients are waiting at a fixed location. For example, material handling systems. You see, an automated guided vehicle or a forklift is a server which is mobile. However, the clients are waiting at a location to be transferred to another location. So please do not think that every queue that we are talking here is a queue like a banking system or a hairdresser shop. The entities are coming and going, and the servers are waiting in a fixed location. There are other type of examples. Now, another term that we would like to learn is the term of calling population. A calling population refers to the potential clients. So if you consider a queuing system, the clients who would like to enter into the queue to get a service are coming from outside the system, right? They are outside the system boundaries. And from outside of the system, they are entering in a queue to get a service. So sometimes clients may also come from another server after completing their operations in that server. They may come from another server to enter the next queue, which is corresponding to some other server. So this is also possible. But I mean, if you consider a simple queuing system, just like a banking system or a hairdresser shop, the clients are arriving from outside of the system. That population from which the clients are arriving is called the calling population. This is the set of potential clients which is outside our queuing system. Okay, from this calling population, the clients are arriving to the system. The calling population can be assumed as finite or infinite. In some examples, the calling population is finite. For example, you may think that in a village, there is a post office, and in that post office, there is only 150 people living. So this means what? The potential number of clients can arrive to that post office is limited to 150 people, no more than that. So the calling population here can be finite, or it can be infinite. Again, let's just give the post office example, but this time the post office is in Kadıköy or Üsküdar. So potentially there are infinitely many people who can enter to the post office on any day. We cannot put a theoretical upper bound. So the calling population can be finite or infinite, as you can see in these two examples. Consider a maintenance system. In a maintenance system, the machines are the entities who are asking for a repair service, right? So machines are the entities, because when they break down, they would like to get a repair service. So machines are the clients which demand service from the crew, and the crew is the server. And here the calling population is finite, because in a manufacturing system, the total number of machines which can break down is limited. However, in a restaurant system in a large city, the calling population there may be assumed as infinite, because on any day or in any period of time, the potential number of customers which can enter into the Hard Rock Cafe is infinitely many. Okay, so we should say unlimited. So for finite and infinite calling populations, we must use different models for the arrival processes. For example, if the calling population is infinite, the arrival rate is independent of the number of clients in the system or outside the system. Because when there is an infinite potential clients outside the system who can enter the system at any time to get a service, even if one entity arrives from that infinite calling population, there is still infinite many other people outside the system. So the arrival rate is not being affected by the number of clients in the system. Even if we have 10, 100, or 10,000 clients in the queue right now, because the number of clients who are outside the system, the size of the calling population is still infinite. No matter what you subtract from infinite, you still get an infinite. The arrival rate will not be affected from that. However, if the calling population is finite, imagine the village example and the post office, the arrival rate is affected by the number of clients in the system. Imagine now the post office in the village, and right now it is 8 a.m. and there is nobody in the post office. So right now there are 150 potential clients who may enter the post office to get a service. So there are 150 people. However, let's just say in the middle of the day, if we count that there are 100 people waiting in the queue to get a service from the post office, then we know that there is only a remaining 50 people living in that village who can potentially enter in the queue. And the arrival rate is going to be less, right? For example, if every villager in that village is in the post office, what would be the arrival rate? The arrival rate is going to be simply zero, because there is not any potential client which can enter the system, right? Because outside the queuing system, there is not any other client which can enter to the queue to get a service. So you see the arrival rate decreases as the number of clients in the system increases if the calling population is finite. However, if the calling population is infinite, no matter the number of people who are in the queue right now, the calling population will always be infinitely many. Therefore, the arrival rate will be independent of the number of clients in the system. Now, we are going to see how we can model such two different calling populations when we are practicing simulation models in Arena. But at this point, let's just say that in both cases, the client who gets the service and departs from the system may return to the calling population as a potential client. For example, in the post office, if a person gets a service and leaves the system in that village, it returns to the village, and after some amount of time, it is again possible for this person to come back to the post office to get another service. So the system capacity is another characteristic that can define a system. It refers to a limit to the number of clients that may be in the waiting line or in the whole system. For example, imagine a hairdresser shop where we have only 2 hairdressers and 2 chairs where we get the service. And there are also 3 other chairs where the customers can wait. So the capacity of system is simply equal to 5. This is the system capacity. So the system capacity is fixed. So no matter the arrival rate, no matter how many customers arrive or clients arrive in a minute or in an hour, it is not going to change anything because the system capacity will limit the number of people possibly to be in the system. Therefore, for example, if the system is at full capacity, if right now there are 5 customers in the hairdresser shop, 2 of them are getting a service and 3 of them are waiting to get a service on the chairs, then a new client who would like to enter the server or enter the queue is going to go back to the calling population to come another time. Or sometimes that customer may be totally lost as well. An arriving client who finds the system at full capacity, if the system capacity is finite, may return to the calling population. Now, there are self-service queues, if you know it. Imagine that we have self-service queues. We do not have any resource limitations. In that case, the system capacity is going to be infinite, right? Because everybody is bringing its own service. Everybody is a server to itself. It is called self-service system. So every client is also a server. So this is a self-service system, and the self-service systems have infinite capacity. However, in most of the realistic queuing systems, the system capacity is finite. When a system has limited capacity, there is a distinction between the arrival rate and the effective arrival rate. Now, the arrival rate is the number of arrivals who demand a service from the server per time unit. For example, for the example that I have given, the hairdresser shop, the average number of arrivals per hour to this hairdresser shop can be 10. However, when the system capacity is full, when we have 5 clients waiting in the system, in that case, most of the arriving clients are just going back to the calling population and they will not be able to enter the system. So which clients can enter the system? If you come as a client and find the system not at full capacity, for example, if there are a less number of clients than the system capacity, then you can enter the system. So effective arrival rate is the average number of clients who arrive to the queuing system and can also enter the system per time unit. So for a finite capacity system, obviously the effective arrival rate is going to be less than the arrival rate, or at least less than or equal to, let's just say. However, for infinite capacity systems, the effective arrival rate and the arrival rate, they are going to be the same, because for infinite capacity systems, anything that arrives can also enter the system. However, when we have limited capacity, only some of the clients can enter the system, which find the system not at full capacity, and the average number of clients who arrive and can enter the system per time unit is called the effective arrival rate. So we are going to go over these concepts in the following lectures, actually, and we are going to give mathematical expressions to denote these variables as well. So let's talk about the arrival process in a queuing system. Okay, and this time we are going to focus on infinite calling populations. How can we model the arrival process if we have infinite calling population. Now, as it says in the first sentence, the arrival process is characterized differently for finite and infinite calling populations. If the calling population is infinite, the arrival process is characterized by the interarrival times of successive clients. Because the arrival rate is independent of the number of clients in the system. Therefore, when we are going to model the interarrival times, we are going to focus on the arrival rate. And the interarrival time is defined as the duration between the arrival of two consecutive clients. The interarrival time of successive clients is modeled with a certain probability model. Now, if the interarrival times are deterministic, so there is this case, the arrivals are occurring at scheduled times, we say. So, for example, in a healthcare system, people arrive by taking appointments, and based on the appointments, we know that the arrival time of the patients are going to be deterministic. So if you have an appointment at 3:30, then even if you come earlier, you will be assumed as you have come at 3:30. So in these cases, if we have arrivals which occur on scheduled times, we say that interarrival times are deterministic, or the arrivals are based on a scheduled appointment time. And there may be a deviation from the scheduled arrival time as well. I mean, even though we have a scheduled arrival times, the people can deviate from their scheduled arrival times in arrivals, and this deviation can be modeled with a probability distribution. So we can say that every client's, every patient's arrival time is deterministic. It is already known. However, there may be an error, either positive or negative. Some people may come earlier, some people may come later. This deviation can be modeled with a probabilistic model. If the interarrival times are random, we say that arrivals occur at random times. So if time between two consecutive arrivals is random, then there is no possible way of determining the arrival time of the customers in any way. So we need to use a probability model, such as exponential distribution, to model the interarrival times in this case. And there may be batch arrivals in such systems, which means at each arrival, more than one client may arrive. So in each arrival, a group of people are arriving and entering the queue. For example, if you consider a theme park like Disneyland, in Disneyland, if you want to enter a queue to get a service from, for example, a roller coaster, you are getting in the end of the queue as a group of people, right? Like for a family. But some family sizes are, for example, large, some family sizes are small. Sometimes you get in that queue with your boyfriend or girlfriend, so this means you are only two people. And sometimes the people arrive there and get in the queue alone by themselves. So at each arrival, a single client or more than one client may arrive. So these kind of arrivals are called batch arrivals. Again, the size of the batch, I mean the time between the arrivals, are modeled with, for example, an interarrival time model. And the size of the batches, for example, the size of the families, can be modeled with another probability distribution, like Poisson distribution. So you see there are many different things that you can model about the arrival process, not just the interarrival times, because at every arrival, more than one customer may arrive to get in the queue. These are called batch arrivals. For infinite calling populations, the most famous random arrival process is the Poisson process. So actually, if the interarrival times between successive arrivals are exponentially distributed, then this process is called the Poisson arrival process. Because you know, if the time between consecutive arrivals is exponentially distributed, then the number of arrivals that occur in a period of time is going to be a Poisson random variable. This was the relationship between Poisson random variable and the exponential random variable. So in a Poisson arrival process, the interarrival times are exponentially distributed. And the assumption behind the Poisson arrival process is what? or the assumption behind the interarrival times to have an exponential distribution, it assumes that the clients make independent decisions about when to arrive. So there is an infinite calling population, and from that infinite calling population, there are many possible clients who would like to enter the system. And though there are some dependencies between couples of potential clients, for example, if I have a job to do in the post office for my family, if I go there as a customer, this means another member of my family should not go. So there's a dependence between a family member of mine when I intend to go to a post office. If I go there, then my family members are not going to go. If I do not go there, then one of my family members is going to go there. Okay, so there's dependence like that. However, if you consider an infinite calling populations, these type of pairwise dependencies will be ignored, and the infinite population is going to behave as if there is a mutual independence. Everybody seems to behave as independent from each other. In that case, the interarrival time to follow an exponential distribution is going to be a natural assumption. So we can explain this like this. If the interarrival times are exponentially distributed, in a certain period of time, the number of arrivals is going to be Poisson distributed. And a Poisson distribution is a limiting case of the binomial distribution, if you remember from probability theory. So in a binomial random variable, we have the size parameter and the success probability. If the size parameter is very large and the success probability is very small, we say that the binomial random variable can be approximated with Poisson distribution. Actually, if you think about a queuing system with infinite calling population, the number of clients who are going to enter the queue in the following 1 hour is a binomial random variable because of the independence between the potential customers outside the system in the calling population. They behave independent, so we assume that for anybody to enter the queue in the following 1 hour has a very, very small probability. So if I ask you, do you have any tasks to do in the post office in the following 1 hour, most probably you will say no. However, some people has it, right? So because of that reason, the probability is very low for a person to have anything to do with the post office in the following 1 hour. However, there is an infinite calling population here. The size parameter in this binomial distribution is very large, and the success probability is very small. Therefore, this binomial random variable, which counts the number of people who are going to enter to the post office in the following 1 hour, is going to be approximated with a Poisson distribution. And if the number of arrivals or the arrival frequencies is a Poisson random variable, then the interarrival time should be exponentially distributed. Actually, the logical proof of the interarrival time modeling with exponential distribution for infinite calling populations is this. Okay, it comes from the Poisson approximation to the binomial distribution. Now, let's just use this notation to model our arrival process further. A1 is the actual arrival time of the first client, let's just say. So if at time 0, the system starts for observation, A1 is the time of the observation of the first arrival, and AI is the interarrival time between clients I-1 and I. So the time between the ith arrival and I-first arrival is AI. And we assume in that exponential interarrival times modeling, we assume that starting from the first index to the infinity, all interarrival times AI, A1, A2, A3, A4, it's a sequence of independent and exponentially distributed random variables with rate parameter lambda. And if the rate parameter is lambda, this means the average interarrival time is 1 over lambda. This is a simple model for the interarrival times or an arrival process for an infinite calling population. Now, for finite calling populations, remember there was an example that we have given, the machine repair problem. How do we define the interarrival time? So when will the next machine is going to ask for a repair service. So depending on the number of machines right now being repaired, which are right now broken down, the remaining machines can potentially break down and ask for a repair service. However, it depends, the arrival rate of new machines to ask for a repair service is dependent on the number of machines which are working right now, which is also dependent on the number of machines which are right now getting a service or waiting in the repair queue. Therefore, we are going to model each machine separately, one by one. So if the calling population is finite, then we need to model the behavior of each client in the calling population separately. So it says for finite calling populations, the arrivals are modeled individually for each potential client. A client is called a pending client when they are outside the system. If we have a finite calling population, and if some of them are right now in the system getting a service or waiting in a queue in the system, the others which are outside the system who can enter the queuing system potentially to get a service are called pending clients. Each pending client, my friends, they wait for a random time to enter the system. So imagine now you are outside the system. You are a machine right now properly working. Therefore, you are not asking for any service from the maintenance crew. So each pending client, each machine, for example, which are properly working, they wait for a random time A to enter the system. So for a random amount of time, they work perfectly, but this is a random amount of time. Then they break down. If this random amount of time is complete, they break down. After breaking down, they get in the queue and they wait for a queue waiting time. This is called WQ. W is called waiting time. And if you write a subscript of Q here, it means queue waiting time. Each machine waits in the queue until one of the servers become idle for the client, because when they enter the queue, they cannot immediately get a service. They need to wait until all previous machines in the queue complete their service so they can enter. But if we have multiple servers, again, we need to find an idle server to enter into the service. And once a machine finds an idle maintenance crew to get a service, then there will be a random time spent to complete the maintenance service, the repair service. And once a machine is repaired, the machine is going to return to the calling populations and become again a pending client. So this is a loop. You are going to wait for an amount of time A, get into the queuing system. Then depending on the number of machines in the queue or in the system, you are going to wait for a WQ amount of time in the queue. Then once your service has started, you are going to wait a random amount of time S to complete your service, and you are going to go back to the calling population and again wait for a random amount of time A to enter the system again. Now, depending on the number of machines which are asking to get a service in the queue, the number of machines which are properly working is also affected. If we have, for example, 50 machines, and if 20 of them are right now broken down and asking for a service and waiting either in the queue or trying to be repaired, the remaining 30 of these machines are going to be called pending clients. And dependent on the number of pending clients, the arrival rate is going to change as well. If there is a less number of pending clients outside the system, then a new arrival into the queue is going to be slow. Therefore, the arrival rate is also going to decrease. Imagine now all 49 machines are broken down, only a single machine is properly working. And you know, the arrival rate for another machine is going to be very, very slow, because there will be maybe a huge amount of time until this final machine is going to break down. Okay, the arrival rate is going to be slow. However, if you consider right now the maintenance servers are idle, there is no machine waiting in the queue, which means all machines are properly working right now. The pending machines, the pending clients are 50 of them. In that case, the time to the next arrival is going to be very short. So it is very probable for one of the machines to break down in a short amount of time. So the arrival rate is going to increase if the pending clients increase, or the arrival rate will decrease if the pending clients decrease. So you see the arrival rate is not a constant value. It is basically a function of the number of pending clients. It depends on the number of clients outside the system, number of pending clients. Therefore, we either use such a modeling for the pending clients for a loop of properly working time, queuing time, and the service time, and again the properly working time. We may create a loop like this for each pending client, or sometimes we can find arrival models which is dependent on the number of pending clients outside the system. Now, obviously, the clients who are waiting in the queue are behaving independently, right? They are free to do anything that they would like if they are human beings. Now, there are also clients which do not have any control over their behavior. If you imagine the queue example where you are the server and the exams needed to be studied are the clients, in that case, the clients do not have any control over the process. Only the server has the control over it. Now, if you imagine a coffee machine where you purchase coffee, then the server is the coffee machine and you are the clients, and actually clients have the control over the process, not the server. Okay, server only provides the coffee at a limited amount of time. Now, in some queues, the clients have independent behaviors such as the following. In the first example, you will see that incoming clients may balk. So what does balk mean? Balking means leaving immediately when they see that the line is too long. For example, when you enter a bank just to pay your electricity bill, okay, for this simple process, you want to go to a bank and you have realized that there are 30 or 40 people trying to get a service there, and you need to wait for all of them just to pay your bill. And what you are going to do is you are going to leave the bank, right? You will not wait there until the completion of the service time of all people waiting in there. And this is called balking. Immediately leaving the system when you see the queue length is too long. And another behavior is reneging. The clients in the queue may renege. What does that mean? Leaving after a while of waiting. Okay, so they wait a little, but then they realize the queue is not moving at all. And they realize that they are going to wait a longer amount of time after this waiting time. And they decide to leave the system. This is called reneging. So the difference between balking and reneging is what? The balkers leave the system immediately when they see the queue length is too long, and the people who renege wait a little first, but then they realize that they are going to wait too long and they renege. And the third one is jockey. The clients may jockey. What does jockey mean? So imagine you are in the airport and you are just in the beginning of the entrance and you need to unlock your belts and everything, and you need to open your packages and stuff in order to pass from the security, right? So there are many queues there. Actually, in logical systems, there should be multiple servers, but a single queue. For example, in the banks, there is a single queue of clients for waiting, and there are multiple servers. So when it is time for you to take the service, you get to the server which is idle. Then if another server becomes idle, the next client enters. So this is a logical queuing system. However, in airports, what we see is there are multiple servers and also multiple queues as well. I mean, sometimes when you get into a queue, you realize that there is a problem and the queue is not moving. And what you are going to do is you switch to another queue, right? To another server. So this is called the jockey operation. So moving from one queue to another, thinking that your queue line is moving slowly. So this is called jockeying behavior. Another one is the queue discipline, and queue discipline basically determines the order of service. How we are going to serve to the clients waiting in the queue. This is defining the queue discipline, and there are many queue disciplines we can define. The most basic one, and which is the most common one actually, that we observe in real life, is the FIFO discipline. So FIFO, first in, first out. Or sometimes we say first come, first served. Almost in every queue that the human beings enter, we observe the FIFO system because it's fair, right? I mean, when you go to a hairdresser shop, obviously you expect the service to be in the FIFO discipline. First come should be first served. However, there are also other type of queue disciplines as well. For example, last in, first out, LIFO. The last entrance to the queue will be served first. So in what systems do we observe this? In inventory systems, right? Imagine an inventory system. There is a box and all new raw materials are arriving to the box and they are put at the top. Then when you are going to process this inventory, you are going to move the inventory from the top, right? So the last entrance will be served first. So in inventory systems, we practically observe this kind of last in, first out queue disciplines as well. And there are also queue disciplines in which we serve the clients in random order. That is called service in random order, which means any client in the queue is equally likely to be taken. They have equal chances to be taken by the server when the server becomes idle. And shortest processing time is another queue discipline, SPT. Actually, when you are studying your final exams, for example, you may think about studying the exam which requires the least amount of time first, right? So you say that, let me study the simplest of the exams first, so let me spend some time for it. This is the exam that is going to take the shortest amount of time for me to study, so I will start from that. So what you are trying to do is you are trying to eliminate the length of the queue as soon as possible, right? So there is a long queue and you want to reduce the length of the queue by serving to the clients, which takes the shortest processing time first. And actually, sometimes it is impossible to determine the time required to study an exam. So it is actually a random amount of time. You will realize it after you study. So this means you are going to take the clients into the server with the shortest expected processing time. So the shortest of the predicted times. You actually do not know how much time you are going to spend. You only know a prediction of them. And another one is the earliest due date. For tasks or for the clients who are waiting in the queue, there is a due date, which means the termination time of their service. So their service must be terminated at that time. That is called the due date. So sometimes you take the customers who has the earliest due date in front of the queue. So if you are, for example, manufacturing furnitures to households, okay, to families, then they are going to give you a due date for that operation. And even if you have multiple operations and your principle is to have a FIFO discipline, first in, first out discipline, sometimes because the due dates of some services comes closer, you first take these processes or these clients in front of the queue. And there is also another queue discipline which is called the priority to certain attributes. For example, the banks are applying this. They provide priorities their own customers, right? So we say, for example, there are two classes of customers. Actually, we have a FIFO discipline in the queue. However, if we have a first class of customer, they always get in front of the queue, in front of the second class of customers. However, there is a FIFO discipline between the first class of customers and there is a FIFO discipline between the second class of customers, but first class always get in front of the second class. So this is a queue discipline which merges the FIFO discipline with the priority discipline. And do not forget about this. If you have a queue with a single server, we know that the clients are going to leave the system in the order which they take the service, right? However, if you have multiple parallel servers, just like in the airport example, now even if your service starts earlier than another people in another server, that guy can finish his service and leave the system before you. So in multiple server systems, the order of entrance to the servers is not the same as the order of leaving the system, okay? So even if we have a FIFO discipline, even if we have a first in, first out queue discipline, in that case, still there is this possible that another client who enters another server at a later time than yours can finish the service earlier than you, and they may leave the system before you, okay? So that may be a possible case. Now, we are going to talk about the service times. So for each client who arrives to the system, once they enter the server, the service time is going to be denoted by SI, okay? Capital SI represents the service time of the ith client. So S1 is the service time of the first client. S2 is the service time of the second client. And that is the time from beginning of the service until the end of it. This is not related with the queue waiting time. It is just related with the beginning of the service and the termination of the service. Now, the service times in some queues may be constant. For example, in a coffee machine, the service times are always constant. Or you can imagine that they are constant because what? The time that the machine fills the cup is always constant, okay? However, there is some randomization because of people paying money to the coffee machine, and it takes some time to do that for different people. However, you can imagine the service time to be constant in assembly lines in which we use robots. So robots always work at a constant fixed amount of time. And another case in which we observe more human behavior, the service times may be independent and identically distributed as well. So, for example, we can say that in a banking system, the clients are served at a random amount of time, which is normally distributed with mean of 5 minutes and standard deviation of 30 seconds. So we may think about an independent and identically distributed modeling for the service times of consecutive customers. So normal distribution is an example. However, there are also other examples. For example, Weibull distribution, gamma distribution, log normal distribution, or truncated normal, it says. Why it says truncated normal? Now remember, a normal distribution is a symmetric distribution, and a normal random variable can also admit negative values as well. So from minus infinity to plus infinity, it can admit any value. Now, in the example that I have given you in a few seconds earlier, we have the location parameter equal to 5 minutes and standard deviation equal to 30 seconds. In that case, that random variable will take a negative value almost improbably. So there will be almost zero probability for this random variable to take a negative value. However, theoretically, it is possible. So because the normal distribution is unbounded in both sides. However, the service times can never be negative. So because of that reason, we need to use a truncated normal distribution, which means we are not going to accept any random variate that is generated negatively. So we truncate the normal distribution from that. If the random variate is negative, we are going to generate another random variate until it becomes a positive random variate. So the negative random variates are not going to be accepted. In that case, we say that we are truncating the normal distribution at 0. We do not accept the values which are less than 0. However, if you carefully choose the location parameter and the scale parameter such that the location parameter is 6 or 7 times larger than the standard deviation, then it is not going to be any problem at all. However, this choice is also depending on the data that you observe. Okay, do not forget about this. If the data tells you to model it with other parameters, then you need to listen to the data, okay? Not yourself. Then you may think about truncating it. Truncation is a solution to this problem. Now, the distribution of the service times, they are not just independent from everything. It may be dependent on the client type. For example, if a client comes to a bank to withdraw money, then he may have a different probability distribution for the service time compared to a customer who comes to deposit money. So depositing operation and withdrawing operation, they are different operations. So for these different types of clients, the distribution of the service time may be different. So one of them can be normally distributed with location parameter 5 minutes and scale parameter 30 seconds. And another one can have another distribution, let's just say gamma distribution with shape parameter 5 and scale parameter 1 in minutes. So when you are going to analyze your input data, you need to think about these things as well. If the service time is different for different type of clients. It may be dependent on the time of the day as well. For example, the service times can be longer when you come closer to the end of the day. Why? Because the servers, they can get tired and they may lose their motivation as they work. Okay, so they may become slower. This means the service times can get longer and longer. So the service times are also dependent on the time of the day or the time of the simulation. And the number of clients in the queue may also change the service rate, the service speed. For example, if the number of clients waiting in the queue get larger, then the servers intentionally may become faster and the service times may become shorter. Now let's talk about the service mechanism. Another characteristic is the service mechanism. A queuing system consists of a number of service centers and interconnecting queues. In each service center, there are C servers. For example, if you think about the supermarket cashier system, in the cashier system, we get into separate queues. There are separate servers and separate queues as well. However, if you, for example, purchase a product from a textile store, there are multiple cashiers. However, there is a single payment queue. There is a single queue there that you wait, and there are multiple cashiers. Whenever you find a cashier idle and you are the next in the line in the queue, you start your payment process. So in these queuing systems, we have multiple servers, but there is a single queue. Okay? So this is a parallel service queue. So the letter C is going to denote the number of parallel servers in a queue. Remember now, there is a single queue, but there may be multiple parallel servers. So when C is equal to 1, we call such queues single server queues. So imagine now in a hairdresser shop, there is only a hairdresser, a single one. So this is a single server queue. Now, if C is greater than 1, obviously C is going to be an integer value, right? If C is greater than 1 but finite, if it is finite, then we call these queues multiple server queues. Multiple server queues. So whenever you are the next client waiting in the line to get a service, whenever you find one of the servers idle, your service starts. So you cannot choose the server that you are going to take the service from. And there are also queues in which we have infinitely many servers. Either a large number of servers, which is too much to count, or we can assume infinite servers. Let me give you an example to an infinite server queue. A self-service queue. A self-service queue is an infinite server queue because every customer comes and becomes the server of itself, right? So the clients and the servers are the same thing in a self-service queue. So imagine now, because every customer, every client brings their own server with themselves, this is called a self-service queue. And we can imagine self-service queues as if they are infinite server queues. So there are infinitely many servers there. And obviously in self-service queues, there will be no queues. Everybody will immediately start their service because they are not going to wait for a resource to be available. They brought their own resources with themselves. What is batch service? A batch service is a service mechanism that serves several clients simultaneously. So let me give you an example to that. Public transportation. Public transportation is a queuing system with batch service because whenever a new metro arrives, it serves to multiple clients at the same time. Or the queues in the theme parks. If you have been in Disneyland, for example, you are waiting in the queue, and when a new roller coaster arrives, which is idle, it serves to a batch of clients, not a single one of them. So that is called a batch service. And in some cases, customer may occupy multiple servers to get service. For example, in health clinics, if you are waiting to get a health service, sometimes you may utilize more than one health employee, right? For example, a doctor and 2 nurses. So in these cases, you may occupy multiple servers. Not just one server, but multiple servers are going to be involved with your task. Now, this is an example in a discount store, basically a store in a shopping center. And this is the queuing system. Now, the clients arrive. So they either shop by themselves by walking around the store. So this is a self-service shopping. So this is the queue one. Or sometimes they choose to speak with a clerk in the store, and the clerk helps them to identify the product that they are trying to find or they are looking for. So if they choose to shop with a clerk, then they need to wait until an idle clerk is available. If it is not, then they need to wait until some clerk becomes available or idle. And let's just say right now there are 3 clerks in this discount store. And even if you choose to get a self-service, after you find the product that you are looking for, then you need to go to the cashier. And even if a clerk helps you, again, after you find the product, you need to go to the payment process. And this is the place where we have only a single server, let's just say. There is only a single cashier. Then you need to wait in the queue until your time comes to take the service. And it depends on the queuing discipline here as well. Most probably a payment process, it has the first in, first out queue discipline. It adapts that discipline. And then you depart, okay? So in this system, you can see 3 different queues, right? I mean, even for this simple system, we have 3 different queues we need to model, even though it is a simple system. So actually, the real life discrete event systems, it is either a service system or a manufacturing system. It doesn't matter. What we observe is basically queues. Different queues, parallel queues, serial queues, and one item, one entity moves from one queue to another until the entity leaves the system completely. So this example on this page is a practical example to show that.